This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Okay, so this is the lecture about detecting gravitational waves. I'm going to try to address some of the issues of principle that people always ask me. Someone asked me during the break, but I'm often asked questions like, if gravitational waves are a distortion of space, and all of space is distorted, and the light is distorted, and so on, how can you detect gravitational waves with light, and all of that. So I want to put all of those things to rest and get you to the point where you have a clear physical understanding of what's going on with the detection of gravitational waves. But then I also want to talk about the kinds of different ways that there are to detect gravitational waves. It's not just interferometers. And then I want to talk about some of the technologies involved, and also, if we have time, a bit about the space technologies. But this is not primarily about technology. This is primarily about the whole enterprise of detecting gravitational waves and how it fits into physics. So this is to remind you of things that I was showing you in the last lecture. This is the polarization diagram drawn in a slightly different way, but you have the two orthogonal polarizations, with the stretching is along the x-y axis, and here where it's tilted to 45 where it's rotated by 45 degrees, and then the tidal representation. This is all to do with general relativity. If general relativity isn't correct, if there's some additional effects, you might have other polarizations, but we know that general relativity is predominantly correct to the 1% level in terms of its predictions of gravitational waves from the binary pulsar kinds of observations, and therefore it's a good description. It's a good basis for providing a description of detection of gravitational waves. If there are small changes at the 1% level, then we'll learn things, but it won't affect whether we're actually detecting the waves or not. So the interferometer again is sitting here with the distortion, and the light comes in here. The interference pattern comes out there, and if you arrange it so that there's nothing, this is a dark port coming out when there's no gravitational wave. Then when you get light, then that gives you the gravitational wave. That's how this diagram of the interferometer explains why we really look to interferometers as a natural way of detecting gravitational waves. But that wasn't the first way that people tried to detect gravitational waves. The first attempt was with the bar detectors. And this is a picture of Joseph Weber, the pioneer of the field, with his first bar detector at the University of Maryland in the United States. Weber actually did consider interferometry. But this picture was taken probably around 1965. And when was the first continuous wave laser? Probably later than that, or around the same time. 1961. So 1961 was the first continuous wave laser, maybe? Yeah. So the technology for laser interferometry for detection of gravitational waves simply wasn't there, and Weber considered it and rejected it and did what he could do at the time. Now, a bar detector operates mainly at its resonant frequency. It's a metal cylinder, aluminum or steel, and a gravitational wave comes in from the side, and you want to think about the interference, that polarization pattern. As the gravitational wave comes in from the side, the stretching in the x direction stretches the bar. And then after the gravitational wave has passed through, the bar has been stretched a little, and it oscillates, and you pick up that oscillation. And he's instrumented it with strain gauges at the point where the strain is maximum, namely the center of the bar. And those strain gauges are supposed to tell you about the excitation of the fundamental normal mode of oscillation of the bar. And so it's that resonant mode, and for a steel or aluminum bar about a meter long or something, the typical frequencies are around the kilohertz. That would be the most sensitive frequency for detecting a gravitational wave. There's an inherent limitation in this, which Weber was well aware of, but this was, after all, just the first attempt. which is that if you want to take advantage of the tidal effect, if you want to make bigger is better, if you want to make it bigger, then it becomes impractical. First, the longest bar that's ever been made is about 3 meters for gravitational wave detection. But the larger you make it, the lower the resonant frequency goes, because it's an acoustic oscillation of the bar. And so if you want to make if you imagine making a kilometer long piece of aluminum, if you could possibly imagine doing that, it would have much too low a frequency, so you can't take advantage of the tidal effect of gravitational waves. So there's an inherent limit on sensitivity. The bars were pushed to around 10 to the minus 19 by cooling them down to very close to absolute zero, liquid helium temperature. And still that wasn't good enough for any detections, and so bars are not being operated now anymore. There have been a few projects to more imaginative ways of doing bar detectors, but it's an inherently limited technology. There was a controversy over Weber, which I'll just mention briefly, which was in the late 1960s. He believed he was seeing gravitational waves, and he published that. He had 2 of these bars, one in Maryland and one in Chicago, and he believed that they were being excited in coincidence with one another. And he published it, and it looked good. And then he also showed that as the Earth turned on its axis, he was getting more coincidences when the bar was broadside onto the center of our galaxy, and therefore it was probable that his excitations were coming from the center of the galaxy, which seemed, even more convincing. But his sensitivity was low, and nobody could understand how there could be so many events with such high amplitude coming from the center of the galaxy. The galaxy would actually be losing a lot of mass if that happened over millions of years. There was skepticism as well. And then it turned out that his data analysis was a bit suspect. He wasn't doing it digitally. He was looking with his eye at 2 different chart recordings, and you can fool yourself with that kind of procedure. You can find things that you want to find, even if you tell yourself you're being honest. And so the only way to test it was to build other bar detectors, and most of the groups that are now in the interferometry business started out building bar detectors to test Weber. And all the bar detectors that were built came up negative. Nobody else saw the gravitational waves. At the same time, Weber continued to see gravitational waves. So then there was, as you can imagine, a terrible period in which this pioneer, this guy who was very clever, wound up being on the fringe. He could not admit that he was mistaken. He tried to invent all sorts of new kinds of physics to explain it. And he died eventually, a rather broken, very sad individual. So it's a sad episode, and it also led to tremendous caution in the field. So LIGO now sets a very high standard for the first detection, of confidence for the first detection, because we don't want to be in that situation. We don't want to fool ourselves. We don't want to be even have people in the community asking us, are we fooling ourselves? We don't want any of that. So Weber's left a legacy, even though it was in the 1960s, that is still affecting the field today. So those were the bar detectors, but most effective detectors of gravitational waves now are beam detectors. They use light, the interaction of light and gravitational waves. And we call them beam detectors, a beam of light with a gravitational wave field. And so I want to talk about this in general, what the interaction between light and gravitational waves is. Now, in a local inertial frame, if I'm in a frame where I can put down a Minkowski metric and I'm freely falling, and I treat the gravitational wave as a small perturbation on that Minkowski metric. I have linearized gravitational waves, and you've studied those. You know what they look like. They travel at the speed of light through this local inertial frame. So they're always locally going at the speed of light. But globally, the gravitational waves distort this geometry of space-time. And can affect the travel time between one place and another that is taken by the gravitational waves. And so beam detectors basically operate on the principle of trying to measure travel time of light through a gravitational wave field. So here's a simple experiment to imagine. And people have imagined this from very early on. Send a beam of light from a freely falling source, your laser or whatever it is, and by freely falling I mean really out in outer space with nothing around. That's what we'll do with LISA. It's not what we do on the ground because we're not freely falling on the ground. So you have to go to next order and ask yourself, does that have any effect? But the principle of the detection is easiest to see if you're in empty space, you're freely falling, and you have a light source. And it goes out and reflects off some mirror and comes directly back to you. So a return trip. How much proper time on your clock, you're freely falling, you have a clock, a nice special relativity clock, how much proper time on that clock is elapsed for that return trip, okay? And if you monitor that and the gravitational waves are going through, you will find that that time changes. And that's a measure of gravitational waves. And that's the principle of measurement that's used in interferometers and other kinds of beam detectors, measuring the variations in that return time. And it's something that's independent of coordinate systems or gauges or anything else. You have a physical object here, which is sending out the light. You have a physical object out there, which is reflecting it, both in free fall, and you have a clock that's measuring proper time locally. There's nothing to do with coordinates in this experiment. And so you can calculate in any coordinate system you want in general relativity what the return time is going to be. It's going to be the same because it's a measurable. It's a coordinate independent measurable. Now there's a very important formula which is called the three-term relation. Very prosaic name for what is the fundamental formula for this whole business. If you have a gravitational wave, so let's suppose the beam of light is going out that way and my mirror is down there somewhere and it's coming back to me. The gravitational wave is coming along at an angle theta to that beam, okay? So it's not a perfectly symmetrical geometry. So there's an angle here which is the direction between the direction of travel of the gravitational wave and the direction of travel of the light. That's what theta is. And the answer for this return time is I'm going to monitor the return time as the rate of change of the return time. So the t here is the proper time on my local clock, and I'm just going to say what's the variation, what's the time variation of this of the return time. And of course, if there's no gravitational wave, so you see a gravitational wave amplitude H plus. H plus is one of the polarization states. I'm taking the polarization ellipse so that there's a common axis, which is when the gravitational wave is going through and the intersection with the light direction. I'm going to take the x-axis in that common plane, and that's the orientation that I take for my polarization. So that's the other polarization component won't contribute to the signal. Only this one polarization does. So I'll call that H plus. And you see, each of these things depends on H plus. If there's no gravitational wave, if H plus is 0, you just get 1. Okay, 1 means the light is coming back always with the same return time. So there's no variation. So you ignore the 1, and you're trying to measure these small variations of order h. The remarkable thing is that there's only 3 times during the signal that are important. So this is the argument of h. H is the value of h at your location, where you're sending out the light. It's the wave field is passing through, and so it's the value at a particular time. And the particular time is this is as a function of the time you sent the light out, not the time you receive it. So t in here is the time when the light was sent out, and then when it's coming back is t return. So t is the emitted time. So here's the amplitude of gravitational waves at the time you're emitting it, and there's a factor here that depends upon a sine of theta. Here is an argument t plus 2L. That's when the light has come back. Now, of course, the return time is affected by h. So there's a small, the return time is maybe t plus 2L plus a little bit of h, but this is already an argument to h. So that's a second order change. So you don't have to worry about that as an argument of h. So this is the return time. This is when the light has come back. So these two terms are the gravitational wave at u when you sent the light out and when you receive it back. And this one, however, is some intermediate time. It's L times L is the path length of the light, the distance out to your reflector, and this is 1 minus sine theta that comes in, and we'll talk a little bit about that. But that's an intermediate time. So there's three terms in here. That's why it's called a three-term relation. That affect. It's not like it's a continuous time. H. It's just three times, three different points in the evolution of that waveform that affect the return time. Let's talk about the geometry. So suppose that suppose that the angle is such that sine theta is equal to 1. The angle is 90 degrees. I should have drawn what the geometry is. Maybe I should. Okay. So I should have had this diagram here. You have your laser here sending out light, and you have a mirror here that's reflecting it back, and this is a distance L, and then you have a gravitational wave coming through with wave fronts. It's a plane wave that's going through like that. The angle theta is the angle between the wave fronts and the path of the light. So you can think of this as the angle theta. So if theta is 0, if theta is pi over 2, then you have a wave coming along here. So theta equals pi over 2 is the wave, the gravitational wave is parallel to the light. It's going along the same direction as the light. So that's when I tilt over here, I make theta equal pi over 2. If you look at what happens when theta is pi over 2, sine theta is equal to 1. The first term has a factor of 0 in front. The second term is a factor of 2, h plus of t. The third term has a factor of 2. And then here, the 1 minus sine theta, that's equal to 1. So this is this is 1 minus 1, that's 0. So the L drops out and it's just a t. And that's the same argument as here. So this term and that term cancel out, and that one is 0, and you get no effect. So when a gravitational wave is going along here, you don't get any disturbance on the light at all. And that's because they keep phase with each other. The action is all transverse, and so there's no disturbance to the light. So that's just to normalize the angle theta for you. The transverse thing here is where theta equals 0, coming in broadside. That's where you would expect the maximum effect. And if so, theta equals 0, the first term is fully there, the second term is fully there, and the third term is absent completely. So you have just the sending out time and then the return time. And it isn't even affected by when the light is bouncing off the mirror. That's interesting. It's just the gravitational wave amplitudes at the emission and return time that matter for the signal. So that's with theta equals 0. But if you have an intermediate theta, then this term, the mirror term, does have some effect. All right, so that's the three-term relation, and it's purely it's a measurable, and it comes out of general relativity, any coordinate system, and it just assumes that the gravitational wave is just a property of the gravitational wave traveling at the speed of light. It has nothing to do with the wavelength of the light that you're using. So sometimes people say, well, is the wavelength stretched? You know, you're doing an interferometry experiment. The wavelength is important. Is the wavelength of the light affected? That's irrelevant. It's all to do with the return time of the light going back and forth. So let's see how that works. This is a bit busy slide. I hope you can see it. I want to talk about different kinds of beam detectors. First is spacecraft tracking, parameters. From the 1960s, people at NASA understood that they're sending spacecraft out through the solar system, and that if you sent signals out to the spacecraft and got them back and monitored the return time, you were doing this three-term experiment. You were doing exactly that experiment. And you might be able to detect gravitational waves like that. In fact, that three-term formula was derived by people working at the Jet Propulsion Laboratory in California for NASA. That was the first time anybody had ever fully explored the quantitative interaction of gravitational waves with light, because that's what they wanted to do, is that experiment. So they first began to do that with spacecraft in the late 60s, early 70s. The Pioneer were involved, but also many of the later missions to the outer planets also carried experiments. The idea was send radio waves out and get them transponded. A transponder is a radio receiver transmitter which tries to send signals back. It tries to send exactly a answering signal when it receives one. It tries to answer with a minimum delay or with a known delay, so you can measure the time of travel and do that experiment. So that's what the transponders were doing. The sensitivity of this kind of experiment is limited by the fact that you're not in vacuum. There's an interplanetary plasma that affects the travel time of radio waves, and so the return time that you get isn't just a function of the gravitational waves. So you have noise from the plasma. And also you have to measure, what I didn't talk about, of course, is you have to measure that return time. So you have to have a very good clock. And so you have atomic clocks at the radio telescopes on the Earth in the Deep Space Network. NASA has instrumented the Deep Space Network with extremely good atomic clocks. Those clocks, some of the best in the world, are stable at some level, like 10 to the minus 16 or 10 to the minus 17, well, probably 10 to the minus 16. And that is the limit. You wouldn't be able to detect variations at less than parts in 10 to the 16 if you have a clock that isn't reliable at those accuracies. And so the typical values of H that you can get from all this are around 10 to the minus 16. The frequency band is 1 over the time scale. So basically you're looking for effects that happen over the time scale and, of transponding and so on. So it's millihertz. And these experiments have been run many times. The Galileo mission was the most recent one, and I think, and they come out with numbers like that, but they have never detected gravitational waves. But that's the classic beam detector of the kind that I just was talking about. There's another variation on this, which is called pulsar timing, which I've talked about, where you get pulses of radio waves from distant pulsars. The radio waves travel through the gravitational wave field, arrive at your location. The trouble is, we're not sending them back. We don't send a signal out to the pulsar, which is after all, thousands of light years away and would be a very difficult experiment to do. So we're just relying on the pulsar giving us these regular signals. So it's not a two-way. It's not an up and back. It's just a one-way thing. But you can do the one-way calculation, and you come out with numbers that are similar, of course, formulas that are similar. And what you get is that H matters both at the Earth and at the pulsar. It's affected by whatever gravitational wave field was passing the pulsar 1,000 years ago when that radio pulse was emitted, and what gravitational wave field is passing the Earth right now. But the pulsars are all over the sky, and the gravitational wave field at the pulsar and at this pulsar and that pulsar are not correlated with one another. So that's basically a noise. So you average over all the pulsars, so you don't pick up any information about the gravitational waves at the pulsars. You only get the correlated effect, which is the gravitational wave at the Earth at the time all these pulses are arriving at the same time. So that's what you're measuring, is the gravitational wave at the Earth. The sensitivity of these experiments is limited by clocks on Earth. Again, your timing, and also it's limited by intrinsic pulsar irregularities. The pulses are some pulsars are quite noisy, and we don't want to use those. But there are some pulsars called millisecond pulsars, which are extremely clean, where the pulse is just coming out with great regularity. The individual pulses can still vary quite a lot, but when you average over about a year with these millisecond pulsars and take out a few systematic trends that the radio astronomers observe, then you get a very clean signal from several pulsars. There's probably about 20 pulsars around the sky that could be used for timing. They're so clean that even with the best atomic clocks, we cannot detect variations, irregularities in their pulses. So we don't know if they're better clocks, but over time scales of about a year, it looks like the pulsars may be better clocks than the best clocks we can build at the moment. So the limits on pulsar timing are set by clocks. And the intrinsic pulsar irregularities are either on the same time scale as the clock irregularities or maybe even better. So as our clocks improve, pulsar timing will improve. But it means that the pulsar timing is still limited around 10 to the minus 16. But I showed you earlier that Alberto Cesana's predictions for gravitational wave backgrounds for pulsar timing are in that range, around 10 to the minus 16. Those are strong background chaotic stochastic signals. So pulsar timing, unlike the signals looking for spacecraft tracking, pulsar timing has a chance of detecting even with the clocks that exist today. The frequency band is not set by transmission time, which is the thousands of years. It's set by the averaging time to get to very stable pulsar arrival times, and that's an averaging time of about a year. So that means that what we're observing with pulsar timing is about 1 to 10 nanohertz. It's below frequency of Lisa band. It's a totally different frequency band than anything else accessible to us. And the sources are these supermassive black holes and their binaries and so on. So if I then go to the next one, imagine building a one-arm detector. A one-arm detector with a clock. It's just like spacecraft tracking. It's the same thing. You send light up and down. It's this thought experiment I just did, and I have a very good clock, and I do that. Why don't I build a gravitational wave detector like that? Why don't I put one of those on the ground or in space? Why go to the extra effort of building two arms for an interferometer? Because it's all very expensive, big vacuum system, and lots of civil engineering, and so on. Well, so the one arm would be the instrument of choice if you could do it. But again, we come down to the clocks. The one-arm detector is limited by the clocks. Both of these things are clock limited. And right now it's 10 to the minus 16. The people who build atomic clocks have great ambitions. They're hoping to be able to construct clocks that get to 10 to the minus 18 in the very near future, 10 to the minus 19, maybe 10 to the minus 20. So I put 10 to the minus 20 here. But 10 to the minus 20 isn't good enough to get to the kinds of sensitivity levels that we need for ground-based detection in the kilohertz band. And so that's why we don't have just one-arm detectors with good clocks. We just don't have clocks good enough. As soon as the clocks get good enough, we may, do that. But at the moment, we need interferometers, and I'll come back to interferometers. But in principle, you could use a one-arm detector with a clock. If you had one, the frequency band would be determined by the arm length. The time up and down would be a sort of sampling time, and also then by the clock stability time scale. So how much the clock's variation.
I have a question. Does that involve putting clocks, very sensitive clocks on spacecrafts that go somewhere far away?
Well, I imagine, for a one-arm detector, I imagine you could build it on the ground, and you just have a clock at the place where you're sending the laser out. And in space, then you would have you would have to face the additional complication of putting a really good atomic clock in space.
Yes, yes. So in fact, I'm curious if we have any high precision clock outside, like maybe there is something on Voyager or Pioneer or something like that.
Yeah, that's right. But those the clocks you can put in space are always 1 or 2 generations behind the ones you can build on the ground. But the next paragraph is relevant to that, because there's a lot of discussion right now of atom interferometry for gravitational wave detection. Now, you know that atoms and particles are, at a quantum level, are waves. There's the wave-particle duality, and so you can imagine constructing an interferometer in which the medium that's being interfered is not light, but is atoms. And people have done this to demonstrate the wave nature of matter. And you could imagine using that to detect gravitational waves in the same way. You'd have a different 3-term relation, and all of that would be different. But in principle, you could detect gravitational waves that way. That's way in the future. Nobody knows yet any practical way of doing that. But the people who do atom interferometry are proposing to build a one-arm space detector in which basically atom interferometry takes the role of the clocks, and you have clouds of atoms that are ejected at both ends, and so you don't have a return time. You have the transition that is being used for the clock is the same, and you pass a beam of light through the atoms at one end, and that imprints a certain state, a certain quantum state. It's all to do with entangled states, and then when you get to the other end, you resolve the entanglement, and hopefully that gives you a higher accuracy than atomic clocks. So that you're not measuring time with an atomic clock, you're just measuring a phase or time transmission differential. So it's not as demanding as having a full atomic clock, but it's something you might be able to do with atom interferometry. So this is I'm a member of a committee for ESA. We've talked about this as a future technology. Some of the people who do this are members of the committee. It doesn't look like it's a technology that we can use on the timescale of LISA, but it is something that might come along for a next generation LISA. So keep your eye on atom interferometry for gravitational wave detection. It's a kind of hybrid between, it's a beam detector, but instead of having clocks, it's using atom interferometry and entanglement. Would be very sexy. So those are all the things that I wanted to get out of the way before I came to the one that is the most effective one, which is the laser interferometer. I wanted to explain to you why we don't do these other things, all of which might seem a bit easier. Well, we do pulsar timing, and it's a different frequency range. But why are we doing the laser interferometers with their 2 arms instead of 1, and all the stuff that's going on? The reason is, you can think of it physically as the second arm is basically the time reference for the other arm. You can't build a clock that's accurate to that level, but if you have 2 cavities that are both being stabilized, then you're beating one cavity against the other, and so your accuracy 10 to the minus 21 or whatever is now how stable can you make those cavities that you can get a time reference or a phase reference out of each of those cavities. The difference, it's not exactly having one of them as a clock and one of them as a gravitational wave detector, because they're both cavities, they're both affected by the gravitational wave as it comes through. And so what you pick up is the difference between what happens in one arm and what happens in the other. So it's a different, the 3-term relation has to be put together in 2 perpendicular ways to get the response to the interferometer out. Okay? But you can do all that. You have a different angle theta and all that. But it's fairly straightforward to work out what the response of an interferometer is. The sensitivity is then limited by how well you can build the cavities. And there's the environment, environmental noise, seismic noise, and so on. There's laser noise. There's the photon shot noise. And I'll be talking about some of these later on. Thermal effects in the mirrors. mirror quality, the shape of the mirrors. All of these things affect how well you can make your cavities and how good you can make your detector. But we do believe we can get detectors 10 to the minus 22 in the next few months, and 10 to the minus 23 or 10 to the minus 24 when we push the technologies even further. The frequency band is determined by the arm length, basically. But it's determined, but it's not equal to the arm length or 1 over the arm length, because we use in these cavities, we use multiple reflections of light, and so we build up a signal in a cavity that's much that stays in the cavity much longer than a single light crossing time of the cavity. So the cavities may have, let's say, a natural frequency range around 100 kilohertz or something like that. But actually, we're measuring 1 kilohertz gravitational waves or 100 hertz gravitational waves by keeping the light in the cavities for much longer periods of time. But it's basically the arm length, and when we go into space, we have much longer arms. We have millions of kilometers instead of a few kilometers, and so then we go to the millihertz band from the ground-based band. There is one thing I wanted to do. Sorry, I should have done before. So let me go back to this diagram, to the three-term relation. I want to also look at the short arm. So I've made no assumption about how long L is in relation to, let's say, the wavelength of gravitational waves. So the wavelength of gravitational waves comes into this because if L is short compared to the wavelength of the gravitational waves, then 2L is a short time compared to the period of the gravitational wave. And you can do a Taylor expansion of H and just keep first order in L, okay? So in the small detector limit, where the arm length is small compared to the wavelength, I can simplify this by doing a Taylor expansion. And what happens when I do that, if you go through all of it, you get something where I just get the first order terms in L. I mean, we've effectively done that. I mean, if I set L equals 0, then all these terms are bound to cancel out. If I have a no arm detector, L equals 0, I'm not going to get any signal. So to first order in L, everything that comes out here will be proportional to L. And so the signal that I'm measuring is proportional to L. And you can understand that in physical terms. For a short detector, compared to the wavelength of the gravitational wave, you're in the diagram where the tidal effect is coherent across your whole detector. And so you're just stretching it out in proper distance and then compressing it in proper distance. Everything is depending about just on L, and that's a simple picture. And that's what we have on the ground. That picture fails if L is much bigger or comparable to the wavelength of the gravitational wave, because then the gravitational waves can be coming through this picture in the way I've drawn them with short wavelengths compared to L. And so the light is going through a fluctuating wave field, and you're getting cancellations. You're getting some effect and it cancels out and so on. And all of that is in this formula. You can rely on this formula. But it means that it's not just a simple coherent expansion and contraction. And with LISA, we're in that regime. LISA's arm lengths of millions of kilometers are longer than some of the wavelengths, or comparable to some of the wavelengths. And that has some effect on LISA sensitivity and so on at the higher frequency end. So that's just something I wanted to point out, that there's, this thing gets simpler if I go to the short arm limit. And that is appropriate for ground-based detection. Okay, so I did all the beam detectors now. Whoops. Now I want to do one other, before I come back to the interferometers, I want to talk about one other way in which people are talking about detecting gravitational waves, which is the cosmic microwave background. And we had last year this excitement from the BICEP 2 experiment that they thought they had seen the signal of gravitational waves. What's going on there, even though cosmic microwaves are microwaves, it's not a beam detector. We're not seeing time variations in the transmission of cosmic microwaves to our detectors. What we're seeing is the imprint of gravitational waves on the polarization waves. So a photon scattering off of the charges that are moving, then that alters the polarization pattern. If the charge is stationary, you'll have a random polarization. But if the plasma is moving this way, you get preferential polarization in the transverse direction. So, so a gravitational wave sort of coherently stretching out the plasma just at the time when the universe is becoming transparent will leave an imprint in the polarization signal of its existence. And that's what people are looking for, and that's a scattering. So it's a bit more like a bar experiment, because the bar, you have a mechanical system being distorted in some way by the gravitational wave, and then you try to figure out what's happening. The microwaves are carrying us the signal of what's happening, but it's not a beam detector. The density perturbations were around 1 part in 10 to the 6 at the time. That's all these nice little fluctuations in these wonderful diagrams that come out of CMB observations. So the gravitational wave perturbations might have had a similar amplitude, and the BICEP 2 is an experiment that would allow the detection of gravitational waves at that sort of amplitude if they were there. And so that's the sensitivity, and the CMB, the sky resolution of the CMB, all these little fluctuation elements that you can resolve, that determines the wavelengths of the gravitational waves, because what you're seeing is in each one of these cells, which is the angular resolution of these CMB experiments, you have to have a coherent gravitational wave signal. So you're seeing the gravitational wave that had the wavelength at the time that fills up that angular region on the sky today. Okay. It's maybe 1,000th of the Hubble horizon at that time. That's what the wavelengths of the gravitational waves are that are selected by this method. And as you know, I'm sure the BICEP team have had to agree that the measurements from the Planck satellite indicate that they didn't have the sensitivity to see gravitational waves because they're background fluctuations, foreground fluctuations, caused by intermediate ionization and so on the plasma, on this cosmic microwave background. So you're not going to see those in the BICEP 2 data, but you may be able to peer through that. The way to get through that is that the foregrounds have a frequency dependence that is different from the cosmic microwave background. So if you can measure over a big frequency range, BICEP 2 only measured at one frequency. If you can measure over at several cosmic microwave background frequencies, you can subtract the foreground signal and try to get below it. And that's what people are doing now. And so if the gravitational waves are at this 10 to the minus 6 level, then in another year or so, we may really have a measurement. But there are a lot of people a lot of theorists who predict the gravitational wave signal is actually 0. So we may get upper limits, and it's hard to predict when we're going to get to that level. But I wanted to talk about that because it's another way of detecting gravitational waves that's quite different from the things that we've been talking about. But now in the last part of this lecture, I want to talk about interferometers. And I think they're wonderful instruments because they involve practically every branch of physics. If you love thermodynamics, then you're going to find a place in a team that builds gravitational wave detectors controlling the thermal effects in mirrors. If you are a materials person, then we really need you to help us with things like suspending the mirrors and constructing the mirrors themselves. Optics, obviously, quantum optics, obviously, everything goes, practically every branch of physics comes in somehow. The principle of the interferometer, I'll come back to, sorry, there are some very interesting things and some myths about interferometers I want to explode a bit later. But let's just talk about the limitations. So environmental disturbances are a big limitation. The two primary sources are environmental and laser shot noise. So environmental disturbances means noise from the ground, and the way we get rid of that is our pendulum suspensions. So we hang the mirrors from maybe a meter or more of suspension, and you know with a pendulum that it's a mechanical filter, that if you wiggle the top of a pendulum at a very high frequency compared to the pendulum frequency, then the pendulum hardly moves at all. If you move the top of the pendulum at a low frequency compared to the pendulum frequency, then the pendulum just follows along with your motion. So it's a low-pass mechanical filter. And what we do in LIGO and was developed in GEO is we have a three-stage suspension, three-ganged pendulum. So we have the product of three filter functions. So we have a very steep fall-off of seismic noise, but basically the turning point is around a hertz. And so we have a lot of noise in the system at a hertz, and then it falls off very fast. And by the time we get to observing frequencies around 10 hertz, we hope, then it should be low enough for us to be able to observe. So the lower limit on our frequency band is set by the pendulum. At the upper end of frequencies, very few noise sources come in. It's actually easy to build, relatively easy to build an interferometer that is isolated and so on. And so at the upper end, we're limited by the amount of laser light that we can put in, because laser light is quantized, and you have photons, and the photons arrive at the beam splitter in a random way, and that causes tiny fluctuations in the intensity of the light that comes out. Even in a perfectly stable interference pattern, you'll have these little fluctuations. And so they have to be that sets a noise limit. That's the noise in our interferometer. That's called laser shot noise. That dominates at the high frequencies, and I'll show you some examples of that. But if you understand these two kinds of noise, you understand the sensitivity of gravitational wave detectors pretty much. And we have ways of attacking this. We have in Virgo, they're even doing a better job for the environmental disturbances. They have six-stage pendulum suspensions. Laser shot noise you can affect by squeezing. You can put the laser light into a quantum state so that the fluctuations in intensity at the exit port where you're measuring it are actually lower. You effectively make the two beams correlated so that the photons arrive back in a correlated fashion. That's called squeezed light, and we're doing that. We did that in GEO, and I'll show you some results of that. And that's being put into the big interferometers in a second stage. So we will get below the standard shot noise limit, but it'll still be laser noise, photon noise that affects it. All right, now here's a quick introduction to how to build an interferometer and how it works. This is a standard, what we call a Michelson interferometer. Laser, beam splitter, mirror up there, mirror down, mirror over there, and photodetector. Light comes out of the laser, reflects, it gets split here into two beams, reflects back, the two beams come back, there's an interference pattern on the beam splitter, some of the light is reflected back in this direction, and this is the constructive interference pattern, and this is the destructive interference pattern that goes out here. Now normally we want to run so that this is zero. Normally we don't want anything coming out here, so that when we get a signal, we go up from zero to something. That's a good signal noise change. And then we're only limited by the noise in our photodetector. But that has the remarkable and somewhat disturbing result that all the light is going back in this direction, right? If nothing's coming out here, then it's all going back here. And it hits the wall and burns a hole in your wall and is lost. So Ron Drever, back in the 1980s, had the wonderful idea of catching, oh no, sorry, I'm getting ahead of myself. The next thing is, first of all, why just put the light just up and down once? Why not put another mirror here and then catch the light? And what I've shown is it bounces up and down just once, which is actually what happens in GEO. But it's slightly different than the other ones. But this is what I was telling you about, is basically you store the light in the arms for longer than the light travel time up and down the arm. Here you're doubling the light travel time with one bounce, but you can imagine lots of bounces. And in fact, in a detector that was a prototype for GEO that was built in Garching near Munich, they had about 40 reflections on a big mirror. They had different spots on this interior mirror, and they had 40 independent bounces before the light came back out. It was really elaborate, but it was also quite difficult to control, and we don't do things that way anymore. There are more sophisticated ways of doing it, but nevertheless, the principle is the same. You store the light here. What that does is effectively increase the arm length. Remember, we're in the short arm regime, and so the gravitational wave is coherent over this whole detector. If you store the light in the arm, it just keeps acting in the same way. It just keeps stretching it out and stretching it out and stretching it out. So as long as you store it for less than about a quarter of the period of the gravitational wave, you get a coherent effect on all those bounces, and the signal just builds up. And so that's the idea of storing light, and that's a big advance. That really improves the sensitivity. It effectively makes the arm length much longer than you could build in practice. I'll come back to that as an important aspect. But then what I said, Ron Drever at Glasgow had this wonderful idea of power recycling. Why not catch the light that's coming back here? This is the light that's wasted. Catch it and send it back in and reuse it. And so if you just catch it in such a way that you make sure it comes back in with the same phase. See, the gravitational wave isn't imprinted there because it's the sum. Here it's the difference, and that's where you see the gravitational wave. But there's no gravitational wave signal in here. And so you just catch it, and you make sure it's in phase with the new light that's coming in, and you recycle it. It's wonderful. It's all very environmental today. It's recycling. And so it's power recycling, and that's what Ron proposed. Also was proposed by Schilling in Munich at roughly the same time. The two of them had this idea independently. They were both working on the things. They realized that they were wasting a lot of light. Why not grab it and bring it back in? Now, if you have perfect mirrors, then you wind up with a laser bomb because nothing ever comes out. There's no gravitational wave down here allowing you, so the light builds up until, but that doesn't, I'll come back to you, but that doesn't really happen because you have losses at the mirrors. You have reflection losses, some scattering, some absorption, and so on. But what happens is that the light goes up in here until it's limited by those reflections and losses. So the losses so this laser is supplying the losses at the mirrors. All right? So that, if you can make your mirrors really good, and we have mirrors with losses of 1 part in 10 to the 6. So that means you can have 1,000,000 times as much power inside the cavities as the laser power coming in. And the laser power is just replacing the losses. So this is a huge improvement in sensitivity, a huge reduction in shot noise. Sorry. No.
Why wouldn't you just put this mirror at the other side of the laser and remove the mirrors of the laser cavity?
You mean remove these mirrors?
No, the last mirror, which was
This one?
the energy-saving mirror, put it to the other side of the laser and remove the mirrors which are within the laser construction.
You mean remove these?
No, in the little box, there's probably some mirrors inside.
Oh, I see. No, you wouldn't do that because then you'd have a huge amount of light going through the laser, and it would distort all the optics and so on. You have to have a really, really sharp line here, and you want this laser to be very, very well controlled. So you wouldn't do that. You wouldn't want all that light going through the laser. It's much better to just adjust the phase with feedback systems so that they're in phase. It's pretty easy to do. I thought you were going to remove these. What actually happens is that this is a good design for GEO. GEO only has one bounce, but then gets all of its sensitivity through this amazing light recycling. In LIGO and Virgo, there's a lot more reflections here, which means that the power is all stored in these arms, and the power recycling doesn't actually come out to here with such intensity as it does with GEO. And that's a big problem for the beam splitter. The beam splitter in GEO has a huge thermal load on it because all the recycled light is going through it. It's a limitation on GEO sensitivity. The LIGO and Virgo designs don't put so much loading on the beam splitter, and that's an advantage. But those are technical things. Okay, so now the next thing that I want to add in is the final recycling, which also Ron Drever invented. No, sorry, that's not quite true. It was before Andreas Freise. It was someone in Glasgow who I'm trying to remember. It wasn't. It was a guy who unfortunately was killed in a climbing accident, and he's no longer with us. And therefore, I'm ashamed I can't pull his name out. But the idea of signal recycling was first proposed in the late 1980s, again in the Glasgow group. And what this does is you put a mirror here at the output port where the fringes are. Now, if there's no gravitational wave, this mirror doesn't do anything. But if there's a gravitational wave, you can tune this mirror, you can make it partly reflecting, and you can put it in a particular place to tune this whole cavity and basically reflect the signal back and forth and build up the signal in a particular bandwidth. So the more reflection you have, the higher the reflectivity, the narrower band you make. You make this into a kind of resonant detector with a narrow bandwidth. If you have only a partial reflectivity, you're shaping the signal a little bit. And this has been done and tested in GEO. It will be done in the big detectors as well, mainly for shaping the signal. But we can improve, if we put in the right kind of mirror, we can improve the sensitivity of these big interferometers in particular frequency bands if we want to go after a particular signal. So all of these are tricks that people have invented, and that's basically what our interferometers are doing. And the final step is, as I've said, we put in cavities here in LIGO and Virgo. You have a whole cavity here instead of just a bunch of multiple reflections. And so this mirror is partly, it's 99% silvered or something, and so some of the light comes back out. This one is totally reflecting. And you build up, most of the power in the arms is in these cavities, and that's how most of these detectors work. Now, I want to correct some misconceptions. Two things I've been saying to you all along, and you probably believe are wrong. And now you can understand why they're wrong. I might not have said this, but you probably believe this. We need freely falling test masses for the mirrors, and that's why we're hanging them, so that they respond to the gravitational wave as it comes along. That's actually not the reason we hang them. We hang them for the reason I talked about earlier, which is to isolate them from ground vibration. We use the mechanical filtering. The reason that they're free anyway, even if I nailed them down, those mirrors, if I had them on a rigid suspension attached to the ground, they would still move with the gravitational wave. And the reason for that is that the Earth is not rigid enough to stop them moving. So you have this gravitational wave, which is a very weak thing. I'm not saying it's a big movement, but it happens on a time scale of milliseconds. The rigidity of the Earth, if you have a station here and a station there that is separated by a couple of kilometers, the rigidity of the Earth is dependent upon pressure waves going through the Earth to counteract whatever stretching is going on. And the speed of seismic waves going through the Earth is rather slow. So when this station moves, this station doesn't get the pull of it until much, much later than a few milliseconds. And so for purposes of gravitational waves, these two stations would actually be free anyway to move in the horizontal direction or to move in any direction. So the reason we suspend them is because we want to isolate them from all the vibrations that are coming through the Earth. All that vibration and everything else that's going on would get in the way of the signal. That means that we're only sensitive in this direction because then that's where the isolation is affecting. going up and down, the suspension will just carry them up and down. So we don't detect gravitational waves in the vertical direction. We're only detecting stretching in the horizontal direction. But it's all to do with the suspension and vibrational oscillations, not to do with the fact that we need them to be freely falling bodies. They are freely falling bodies in this time scale region. The second misconception, which I certainly am guilty of having said to you, is, bigger is better. We build our detectors kilometer size on the Earth in order to get them to be very big and build up a signal. Well, I've already told you why that's wrong, which is the fact that we have this multiple reflections in here that increase the length, the arm length. So I could actually build GEO 600, let's say, is 600 meters compared to 3 kilometers. I could build up the same signal sensitivity in GEO 600 by just having that many more reflections, okay, and doing my optics better. Why we build the thing, why it's better to have a bigger detector than a GEO 600 is that there are other noise sources. And particularly we have the vibration noise that comes in through the suspension. We have thermal vibrations in the mirrors and so on. And the more times you bump into a mirror, the more times you pick that noise up. And so we want mirrors to be far apart so we can store light in those arms, but we minimize the number of times the light is in contact with the mirrors. And in GEO, the light contacts the mirrors 4 or 5 times more often, and so we have a background of noise that is much harder to get rid of than in the larger detectors. And if we could build a 10 kilometer detector like we plan to do with Einstein telescope underground, then we would reduce that effect even more. So that's the reason for going long arms, is to minimize the mechanical noise inputs when you're contacting the mirrors. Okay, so that was in order to get rid of that. Now I have only a couple more things to do. Quantum noise, for example, is what I talked about. This is an introduction to how we do squeezing. Here's the laser interferometer, the same diagram as you've seen. This is actually what GEO looks like. This is a diagram of GEO, which is where we introduced squeezing. So GEO has just one reflection, and it doesn't have the interior mirrors and so on. So it's a folded arm. And all the light goes through the beam splitter, and all the power is on a power recycling mirror. And there is actually a signal recycling mirror not shown in this diagram because it's not relevant to what I'm talking about. But basically, this is a closed system, except it has it's open to the rest of the world only here. We talk about the signal coming out in the interference pattern, but there's also stuff coming in. In particular, there's the vacuum. The electromagnetic vacuum is coming in this way. It's the only way it can get into your detector. And the electromagnetic vacuum at a quantum level is noisy. It has the 0-point fluctuation of all the quantum modes of your electromagnetic field. And so those 0-point fluctuations get into here, and there's a way of formulating the shot noise problem, the noise of photon arrival times and so on that I was talking about. There's a way of formulating that problem in quantum mechanics entirely in terms of this noise as a smooth classical field with this noise imposed upon it, which is coming into your detector. So to control this, to do squeezed light, so that's the vacuum noise that's, I've just said, is coming in. You put a mirror here. You put an apparatus here, you put a mirror here, and you stop the vacuum coming in a raw way, and you squeeze it. You turn it into a different vacuum state with correlations. You're not getting around the Heisenberg uncertainty principle, but you're changing the state variables, the conjugate variables where the uncertainty principle applies, and you're squeezing the uncertainty on one of them. You're putting all the noise from the vacuum into something you don't measure, because we're not measuring the vacuum. We're not interested in the vacuum. We put all the noise into one place, and we measure the variable that has had its noise squeezed, so it's lower noise. We measure that variable, and we make sure that variable is containing the gravitational wave signal, because we're not interested in anything but the gravitational wave signal. We don't want to make a quantum measurement. We want to get rid of the quantum noise into one quadrature, and in the other quadrature have a very quiet quantum quiet background, so that's where the gravitational wave signal is. And that's what's going on with squeezed light. The light comes in, the vacuum fluctuations are squeezed so that they don't come back out in the interference pattern. What comes back out in the interference pattern is much quieter. So does that work? Well, in Geo 600, the black line, this is one of these sensitivity curves like the one I showed you before. The black line is what is before squeezing. It happens only at high frequencies where the shot noise dominates. It doesn't happen down here where we have vibration noise. But the shot noise is dominant here. And here, after we introduce squeezing, this is the sensitivity to gravitational waves. So that we've reduced the noise in the gravitational wave observation channel here by a factor of perhaps 2 or something like that. The most we've got is factors of 2.5 or 3, I think, for the reduction in noise. And that's a very significant thing. If you can reduce your noise by a factor of 2, you have improved the reach of your detector by a factor of 2. You've improved the volume it surveys by a factor of 8. So you have improved the number, you get 10 times as many gravitational wave sources by just introducing squeezing by a factor of 2 or 2.5, something like that. So that's a really significant improvement in your gravitational wave detection ability. And it's all done with the deepest quantum mechanics, totally mysterious. This is what the apparatus really looks like. This is the Geo vacuum tanks for the interior mirrors and the power recycling mirror and all of that stuff. But all of this is the table that contains the squeezed light apparatus. And so it's not a trivial job to impose this squeezing on the vacuum fluctuations, but that's what happens. I think I should stop there. It's 9:30 now, and I think I should have tried your patience. The one thing that, maybe I'll show you one more thing. I just want to show you something about the LISA slideshow. Ah, that's not what I wanted to do. This is a and now I've lost the slide I wanted. Here we are. That's it. This is the LISA Pathfinder again. I just wanted to show you the pictures of the LISA thing. LISA, this is Pathfinder. It's a big can with 2 test masses separated by ½ a meter. So inside this is the diagram I showed you earlier, which all that, those free test masses that are sitting there. And the interferometry would just happen along here. We're just trying to measure changes in distances and so on over that very short baseline. This is the optical bench. The interferometry is very similar to what we'll do with full LISA. It's just the separation isn't good. It's not a gravitational wave detector, but a good test of the principles of the interferometry. But otherwise, it's very similar. The LISA interferometry, we don't have cavities. We just send a signal up and then come back. We're measuring a return time. But because you can only focus a beam of light narrowly, but it still spreads out over 1 million kilometers. It spreads out huge. It's tens of kilometers wide, and compared to the spacecraft that's receiving it. So there's a big reduction in the amplitude of received light from the laser from one to the other, and we only have 1 watt lasers. So the light that's received at one end is very small. If we just reflected it back with a mirror, we'd never get any photons back at all. So it's transponded. So we're doing what the spacecraft people do. We have a receiving system that senses the incoming light and has an independent laser that's slaved to the incoming light and sends back with the right phase and so on. So it's an active mirror. It's an amplifying mirror, a transponder. That's the heart of the LISA technology, and apart from that, you get it's a 2-arm, it's a 2-pass, 1 up and 1 down apparatus. It's the same as the as the three-term relation, only in a triangular array. You can put together any two of those arms to form an interference pattern, so we get three independent gravitational wave signals. And they really are independent if the gravitational waves are short wavelength compared to the arms, because they're affecting all the arms differently. So we get a lot more information about the gravitational waves that way. But basically the technology is the technology of LISA Pathfinder plus this transponding to get the right intensity, and that's how LISA will work. Okay, so I think I should stop there and we can take questions.
Do you use solar cells as a power source for that satellite?
Yes.
Okay, I still don't understand one thing. You said that wavelength is not important, only return time, but when I see interferometer, I can't imagine how wavelength may be not important. So could you just explain it a little more?
You mean the wavelength of the light?
Yes.
Yeah.
Yes.
Well, I can do white light interferometry if I'm really good. If I have an interferometer with exactly equal arms, then every wavelength will come back and interfere with itself in the right way, and I'll get a white light interferometer. And it doesn't matter what my wavelength is. So the wavelength is not relevant.
And inside this interferometer, you are measuring the return time, or it's
The interferometer measures the differences in return time. So the light goes out, comes back, and if there's a change in the transmission time along one arm relative to the other, then you get a slightly out of phase signal.
Now I see.
Now, the wavelength is important in terms of how accurately you can measure it, but it's not important for the effect of the gravitational wave imprinting on it.
Okay, thanks.
When I'm talking now about an earthbound construction with pendulum suspension and so on, wouldn't, particularly if I send around the laser many times between the mirrors, wouldn't the pressure of the photons already move the mirrors?
Yes. Yeah. So there's a balance. We have to worry about those things. There's a balance. That's one of the things that I didn't talk about, but is very important. There's photon pressure with a lot of photons on the mirrors is traded off against the accuracy with which you can measure the photon shot noise. In our present regime, we're limited by shot noise. But if we pump up the laser power to the final levels that we expect, about 100 watts or 200 watts laser input, we will be in a trade-off situation where we have to worry about those things. Yeah. And then people have thought of there are many more optical tricks that people then think about to try to get around these things. And squeezing is one of them, but yeah, it's an important thing. Sorry, there's a question back there.
Does this signal recycling increase shot noise? Because less light is going to the detector.
No, so you mean less light is coming out to the photodiode? Yeah. No, because in the end, because you have a cavity, in the end you're getting you're getting roughly the same amount of light coming out, and the shot noise anyway is in the interference pattern at the beam splitter. It's not. It's the randomness of the interference. It's not the photon counting at the photodiode. It's all at what's happening at the beam splitter.
And could you explain this concept of this squeezed light? I mean, to eliminate this vacuum noise a little bit once more. I didn't get it right.
In the standard description of light of the electromagnetic field, you can construct a Hamiltonian based on the number of photons, for example. the uncertainty principle, I think it's right, but I might be oversimplifying here. The uncertainty principle, there is an uncertainty between intensity and time, or the number of counting and the ability to measure the time arrival of things, and so if you pump up, if you have a lot of photons, then you improve your measurement of time, the time arrival of anything.
Number of photons and phase.
It's the phase, isn't it? Yeah, it's not the time. It's the phase. Yeah, that's right. Thank you. But you don't have to have those as your conjugate variables in constructing the description of the electromagnetic field in the cavity, and you can go over to a description in which the two conjugate variables are the two outputs from the beam splitter, the constructive and the destructive interference, basically intensities, which are independent of each other. They depend, and they're a function of this phase shift that you get between the two arms. So in principle, you could put all the noise into all the quantum noise. So having constructed those two, then it's a question of, can you find the technology to change the Heisenberg uncertainty circle into an ellipse in such a way that you reduce the uncertainty in the intensity of light that's coming out the beam splitter to the detection point, and at the cost of increasing the uncertainty of the light that's going in the other direction back to the power recycling mirror. So you're trying to reshape the Heisenberg uncertainty ellipse in the new variables. And so basically you try to choose variables that correspond to the two different exit paths from the interferometer. How you do that, I'm at a loss to describe myself. That's where all those mirrors in that thing are coming in. But the principle is to try to make the part of the light that's carrying your gravitational wave signal as quiet as possible. And as long as you make that one of the conjugate variables, then it's just a matter of how can I reshape the uncertainty ellipse. I don't get around the uncertainty. I just put more uncertainty in one of the conjugate variables and less in the other.
Perhaps a stupid question. Would it be a good idea to put a really, really long light fiber inside a satellite? So, the total length would be really large and there would be no noises from earthquakes, from sound or anything.
Yeah. So people have thought about that. One of the problems with there are a number of issues. One is that the light in a fiber doesn't go at the speed of light, so you have a material problem. But the second one is that fibers are intrinsically imperfect. There's a lot of scattering compared to what we can do in a vacuum cavity. So the amount of light you can store is limited. Plus, there's a lot of thermal effects in these materials. So even if you have no external disturbances, you will get little popping and all sorts of little thermal disturbances. We see this with the coatings on our mirrors. We see when we turn up the light intensity, we see lots of little glitches in our data that we think come from thermal effects which are not in thermal equilibrium. They're little domains that may release or change or something. But in a fiber, the way fibers are drawn, that happens a lot. So at the moment, it's much better to have just a vacuum cavity than something actually, a material system actually containing the light. But it's not a stupid question.
The mirrors up on the moon, which would make for a really very long provided the atomic clocks become better?
Actually, yeah, the people who do laser ranging to the moon have talked about setting limits on gravitational waves in that particular frequency band. The problem is that the reflecting area of those mirrors is very small. So the light that you get back is they can count the individual photons. So photon shot noise is the dominant noise, so that limits the sensitivity a lot. If we put up huge mirrors on the moon, then that would be something. But then you also have the laser light traveling through the atmosphere and all sorts of other noise things that are imprinted on it. But people have talked about using it.
Are there further questions?
Okay, good. Thank you.
So it's wonderful that we had such a masterful conclusion to the lectures of the school. Thank you very much.
Right, thank
so
you.
to me it's zero surprise that students complimented your lectures a lot already in the break. And I'm sure they will remember the school for a very long time and
Thank
your
you.
lectures.
Oh, thank
and
you.
this is for you to remember the lectures for the lifetime of this cup.
Oh, right, thank you very much.
And we also have, and it's a happy coincidence that your German is so good. So this is actually Kepler's Astronomia Nova with lots of comments and so on. And
Oh,
it's a
great.
very
Oh, this is
highly
wonderful.
recommended book.
Oh, wonderful. That's a pleasure. Thank you.
Thank you very much.
Thank you very much.